Okay, so today we are going to be focusing on our 3.2, which is slope of a line. And our objectives are as follows. We're going to learn how to find the slope of a line, what the definition of a slope is, and why don't we just jump right into it so that you guys have a solid understanding of it. Definition of slope, and we'll go over this more formally on later slides, but it essentially just means our rise over our run when it comes to a linear graph. If we're looking at our slope-intercept form, our y equals mx plus b, our m represents our slope. And then from a technical perspective, if we were given two coordinate points, let's say we were given x1 comma y1, this is like our first coordinate point. And then let's say we were given our second coordinate point, we'll call x2, y2. Then we can determine what our slope is by taking the difference of our y values and dividing them by the difference of our x. So what does that look like? It's simply our change in y, so y2 minus y1, all over x2 minus x1. And we'll practice this a lot throughout our lesson today. The second objective, we'll be able to graph these linear functions or just these lines in general, given a point and a slope, hence our point slope formula. So again, I'm sort of like foreshadowing our notes to come, but it's always good to enforce this ahead of time. So our point slope formula is simply y minus y1 is equal to m in parentheses x minus x1. And why is it called point slope? Well, we're given a point, our x1, y1, and then we're given our slope, our m. Our third objective, graphing a line using the slope-intercept form, which we have up here. So maybe what I'll do is I'll just highlight it up here. Or I'll box it. And why is it called our slope-intercept form? Well, once again, we have our slope. And then we have our y-intercept, which is our b value. Our fourth bullet point, we're going to be able to interpret applications of slope-intercept. So how do we utilize this in a real-life situation? And then our last bullet point really hones in on the relationships of parallel lines and perpendicular lines. And once again, sort of give you a preview. When we're dealing with parallel lines, we want to make sure that the lines have the same slope, but different y-intercepts. So this is a definition. Our lines have the same slope, but a different y-intercept. And why does it have to be a different y-intercept? Because if they had the same slope, and the same y-intercept, then it would just be the same exact line. And if the line is identical, it's not parallel. The definition of parallel is it never touches one another. Whereas finally, we have, running out of colors here, use red. Perpendicular lines have negative reciprocal slopes. We learned about negative reciprocals maybe a few lessons ago, so now it's popping up again. Our lines that are perpendicular, and then I'll show you a cool short script for perpendicular. It's an upside down capital letter T. Why is that? Well, it forms perpendicular lines form right angles. Have negative reciprocal slopes. They could also have the same y-intercept here. I'll give you an example. Let's say you have a slope that is 1/2. What's the negative reciprocal of 1/2? Well, you flip it and then you multiply it by -1. So 1/2 versus -2. Again, there'll be a slide on all of these definitions, but having them all on one slide and just getting familiar with them before we start the lesson, I think is always helpful. Okay. So let's first talk about our slope more formally. What is our formal definition of a slope? Again, it's our rise over our run. It measures that vertical change, and the run measures that horizontal change. Vertical change on an X and Y coordinate plane is just our Y axis. So you're taking the difference between your two Y values, your Y2 minus Y1. Whereas your horizontal change is your X axis. You're taking the difference between your two X values, your X2 minus X1. Hence, what is slope? Change in Y over change in X. And below are just the step-by-step procedures when you are taking the slope between 2 points. The key is really identifying what's your X1, what's your X2, what's your Y1, what's your Y2. So let's now practice this from a graphical standpoint. Anytime you need to identify the slope from a graph, it's a really good idea to look on the graph to see where it hits the corner of one of the squares because you know what point that is. So that red point is just 0, 5. And then go again. I think the next corner is over here. And this is 3, 3. Now, you can utilize the technical perspective of your change in Y over your change in X. Teach you 2 different ways to do this. This, I think, is the slower way to go about this. This is your first X, your first Y, your second X, your second Y, and then do the change in Y over the change in X. So we're looking at Y2 minus Y1 over X2 minus X1. This is 3 minus 5 over 3 minus 0, which gives us negative 2 over 3 to be our slope. And you would definitely use this procedure if you're just given the 2 points and not the graph. But if you're actually given a graph, I would just use your knowledge of rise over run. How many times or how many units are you going either up or down and then running across? Well, we're going down 2, so minus 2, and then you're running across 3, 1, 2, 3 to get to your 3, 3, which means what is your slope? Your slope is negative 2 over positive 3, which is exactly what we got when we calculated it on that right-hand side. And we're done. Some more formal notes. We have the slope of a horizontal versus the slope of a vertical line. Horizontal lines have no slope, right? It's just 0. We're looking at a nice straight horizontal line. There is no change in our y values or our x values. Well, the change in our x is just 0. I'm sorry, the change in our y is 0. Whereas a vertical line, the change in our x is 0. And because 0 is in our denominator, any 0 in the denominator makes our fraction undefined. So we have an undefined slope when we're looking at any vertical line. So all vertical lines have undefined slopes. All horizontal lines have slopes of 0. Any horizontal line is written as y equals some number. Any vertical line is written as x is equal to some number. Many students make that mistake. They confuse the two. All right, so let's practice drawing out some vertical and horizontal lines. So our first one is we want to find the slope of x is equal to 8. Is this a vertical or is this a horizontal line? How many people? Yeah, it's vertical, which means what's our slope? Yeah, therefore, our slope is undefined here. What about y equals negative 5? Yeah. Therefore, what's our slope? Good. Some more formal definitions. Haven't really covered this in our objectives earlier, but anytime you're looking at a positive slope, you're always reading your graphs from left to right in math. So if you have this nice, beautiful XY coordinate plane, and I were to draw a random line on this graph in red, we'll call this line L. We want to read this from left to right. And from left to right, you'll notice that we are going up a hill. We're going up, then it's going to be a positive slope. If we read this graph, and we are now looking at a line where from left to right we're going down a hill, then our slope is going to be negative. And once again, we covered this on the slides just before. If we have a nice horizontal line, our slope is 0. And then if we have a nice vertical line, our denominator is 0, which makes our slope undefined. When we are given 2 coordinate points and we're not given a graph, this is how we find the slope between 2 points. Our change in y over our change in x. y2 minus y1 all over x2 minus x1. And so now let's practice that. We're given these 2 points and we want to find the slope through the line that contains these 2 points. I always like to label my x1s and x2s. This is going to be my first x. This is my second x, because every coordinate point is in the form of x comma y. And then this is my first y coordinate point. This is my second y coordinate point. What is my formula for slope? Change in y over change in x. That triangle is just, it stands for change in. It's from the Greek alphabet, which is our delta letter, which means finding the change, finding the difference between 2 values. So we're finding the difference between our 2 y values over the difference between our 2 x. And so I'll color code the first one. We have our y2 minus y1 is equal to our x2 minus our x1. So we're looking at 4 minus -3 all over -7 minus -2. And then we want to simplify. 2 negatives right next to each other give us a positive. So in our numerator, we have 4 plus 3, which gives us 7. And in our denominator, we have -7 plus 2, which gives us -5. I always like to put my negative in the numerator, but if you wanted to just keep it as 7 over -5, you would get full credit for that. And that's it. This is our slope. Right. We have another slide of notes. And this really hones in on our point slope formula. We want to find our line given that we have a point and we have a slope. And so what is our point slope formula? We have our y minus y1 is equal to m in parentheses x minus x1. Again, we are given a point here and a slope. And so anytime you want to put it in this form, you want to look in your problem to see if you're easily able to calculate the slope and have a point. So what happens in a situation like this? You're either going to be given 2 points in the problem because you can just do change in y over change in x. That'll give you the slope. And then you can choose either one of those points to plug into your point slope, simplify, and you get your answer. Another situation is even more straightforward. They just physically give you the slope and a random point on the line. And then you just use your point slope, plug it in, and you're done. So let's test it out with this example 4. We have graph the line passing through this point. They give us a point, and what do you know? They also give us the slope. So what are we using? Our point slope formula. Y minus y1 is equal to m in parentheses x minus x1. When you practice this over and over again outside the classroom, you will start enforcing these formulas in your head. And so, yeah, you're memorizing them, but you're memorizing them through practice, through a bunch of repetition. It's called rote learning. So let's plug this in. Again, my 1 comma negative 1 is just our x1 comma y1. So we're looking at y minus our y1, which is negative 1, is equal to m, which is given to us as 3/4, in parentheses x minus x1, which is 1. Once again, I'll color code. I won't be color coding all of these problems, but the beginning ones, I just want you guys to get a little bit more comfortable with it first. Two negatives next to each other give us a positive. So we're looking at y plus 1 is equal to, and now we can go ahead and utilize our distributive property, 3/4 x minus 3/4. If they asked you to just find the equation of a line, and they didn't specify to put it into slope intercept or point slope, then once you get to this part, and I would simplify the two negatives. So once you get to really y plus 1 equals this whole thing, 3/4 in parentheses x minus 1, you get full credit. You'd be done, and you can move on to the next question. But if they told you to graph, which they do in this case, or put it into slope intercept form, you really want to get it into your slope intercept first so that you can really identify what your slope is and what specifically your y-intercept is. So this step right here is we are simplifying to put into slope intercept form. So what are we going to do? We're going to subtract 1 from both sides. Now we're back to subtracting fractions. What's 1 as a fraction? It's just 1/1. We want to get that same denominator. So we need to multiply that by what? Yeah, exactly. By that fancy form of 1, 4/4. So we're really looking at negative 3/4 minus 4/4, which gets simplified to what? What's negative 3 minus 4? -7, right? Because I owe you $3 and now I'm owing you another $4. So how much money do I owe you in total? I owe you $7. And that's it. So we've officially converted this into our slope intercept form, which means now we can easily identify what our y-intercept is. We already knew our slope was 3/4 from the problem, but more specifically, what's our y-intercept? What's our b value? It's that -7/4, right? And definition of y-intercept is when x equals 0. So if we wanted to write this in coordinate form, it would just be 0, comma, -7/4. And why is that so important? Well, anytime we're graphing a line, we need to start with the y-intercept and then use the slope from there. So -7/4 is about what? As a mixed fraction, it's -1 and 3/4, right? So between -1 and 2. And now from here, we want to utilize our slope up 3 over 4. So we're going up 3. So we have 1, 2, 3, and then over 4. So this will be 1 point. Anytime you're graphing a line, you want at least 3 points, 3 to 4 points. And then we're given a point or 1 comma -1 that we can easily plot right over here. And that should be enough. So we'll connect the dots. Draw your arrows. The X and Y axis or axes are already labeled. So our last step is just to write the equation of your line on your graph. Y is equal to 3/4 X minus 7 over 4. And that's it. We're done. Any questions? Now we have our formal definition of our slope-intercept form. Slope-intercept. So y equals m, which is our slope, x plus b, which is our y-intercept. I know it's down here, but I'm going to make it nice and big up here. We have our slope. And then we have our y-intercept. So let's do some examples involving slope-intercept form. So in example 5, we want to identify the slope and the y-intercept of these two given equations. So the first one, lucky for us, it's already in our slope-intercept form, which tells us what's our slope here. Good. And what's our y-intercept? Got it. And in coordinate form, what is that? This is our y-intercept. What's our definition of y-intercept? When x equals intercepts the y-axis. So when x is equal to 0. So as a coordinate point, our y-intercept is just 0, comma, -2. I want to use the same color. So we had B as our y-intercept and purple is our slope. Part B, we are given an equation in standard form. Standard form is just like some form of x plus some form of y is equal to a constant. But we want to put this into slope-intercept form so that we can easily identify both our slope and our y-intercept. So we're going to use some inverse operations here. For x plus 3y is equal to 9. Let's go ahead and subtract x from both sides. And now we're looking at 3y is equal to -x plus 9. Now we're going to go ahead and divide both sides by 3. And we're going to separate that fraction on that right-hand side. So we're looking at -x over 3, which is really just -1/3 x, plus 9 over 3, and 9 divided by 3 is just 3. Now that it's in our slope-intercept form, we can easily identify what our slope is. What's our slope? -1/3. And then what's our y-intercept? 3. In coordinate form? Good. And we're done. Any questions? All right. Take a look at example 6. We're asked to graph this equation y equals negative x plus 4 using its slope and y-intercept. So what's the slope here? M is equal to? Remember, slopes are only numbers. Yeah, so it's just -1. And -1 as a fraction is what? -1 over? Yep. This is our rise over our run. What's our y-intercept? Yep. As a coordinate? Yep. Anytime you're graphing, you want to plot your y-intercept first, and then use your slope to plot additional points. So let's plot our y-intercept 0, 4. Use our slope to plot additional points. -1 over 1. So instead of rising, it's a negative. So we're going down 1 and then to the right 1. Down 1 to the right 1, plot your point. Do it again. Down 1 to the right 1, plot your point. Do it one more time. And then we can go ahead and connect our dots. Put arrows on the end of our line because lines go on forever. And then finally, write out the equation, -1x plus 4. We already have our x and y axes labeled, and we have a proper scale set in place. This would yield full credit on any quiz or future assessment. And we're done. Questions at all? No? Okay. So I might have 3 students read these paragraphs for me. Let's do maybe blue, green, and pink. So I might have, let's see, Gabriella, I'm going to have you read blue. Angel, I'm going to have you read green. And then Calvin, I'll have you read pink.
Many of your word applications are modeled by linear equations. We will take a look at a few applications here so you can see how equations written in slope-intercept form relate to real-world equations.
Yeah.
Usually when a linear equation models use real-world data, different letters are used for variables instead of using only x and y. The variable names remind us of what quantity are used.
We often need to extend the axis. Trying to put in systems to figure positive and negative numbers.
Great. Thank you, guys. Okay. So this is our first sort of real life situation. We're going to be dealing with our conversion between Celsius and Fahrenheit here. And so we're given the equation of Fahrenheit is equal to 9 fifths Celsius, which is C plus 32. And so our first part of the problem is we want to find the Fahrenheit temperature for a Celsius temperature of 0. So what do we do in a situation like this? Well, we're given our Celsius, our C is equal to 0. So we can write that down. And that tells us that, okay, if our C is 0, we're just going to plug in 0 where we see C and then solve for our F. So F is equal to 9/5, parentheses, put in 0 for our Celsius. And you could put in the units, you don't have to. You just have to definitely have it at the end, plus 32. And then we solve. Anything times 0 is just 0. So we end up with 0 plus 32, which means our Fahrenheit, when our Celsius is 0 degrees Celsius, we have 32 degrees Fahrenheit. And we're done. Right. Let's answer another very similar question. We want to find the Fahrenheit now when our C is not equal to 0, but our C is equal to 20. The same exact concept. Wherever you see a C, we're now going to replace it with 20. So we're looking at 5, or not 5, F is equal to 9/5, in parentheses, 20. And because we're multiplying by a fraction, 20 as a fraction is just 20 over 1. I'm going to put that in. So we're setting ourselves up for success in the future. And now we want to multiply these two fractions, but instead of multiplying, I notice that we have a 5 here and a 20 here, and 5 goes into 20. So let's make these numbers a little smaller. 5 goes into 5 one time, and 5 goes into 20 4 times. Now let's multiply across. So now we're just dealing with our 9 times 4, which just gives us 36. And then 1 times 1 in our denominator is just 1. So we're just adding 36 and 32 together, which tells us that when our Celsius is 20 degrees, our Fahrenheit is 68. And we're done. Part C asks us to interpret the slope and the f-intercept of the equation. The f-intercept is essentially, right, our y-intercept. So what's our slope here? It's our m value. M, it's really MC in this case, plus B, and I'll write it as y equals mx plus b all the way at the top. So our m here is just 9 over 5. And then our f-intercept, aka our y-intercept, is our b value, which is 32. As a coordinate point, that's just 0, 32. And they ask us to interpret this. So we'll interpret it verbally. Well, our intercept tells us our initial value, our starting point. So when our Celsius is at 0, our Fahrenheit is at 32. And from our initial, what is happening? What is our change? What's our slope? Well, we're going to be going up 9 and over 5. We have a scale of 9/5, which is changing as we increase our values of our Celsius. Lastly, we want to graph this equation. So always start out with your y-intercept, 0, 32. I put in a little squiggly since we're dealing with a very large initial value at 0, 32, but then our slope is fractional. So we want to go up 9 over 5, 9/5 as a mixed fraction is 1/4, which is like 1.8. So we're going up 1.8 over 1. And so what do we have here? These are increments of 2, so it's like just below each tick mark. And I'll make them a little small. So over 1, up 1.8, over 1. We'll do maybe one more. Up 1.8, over 1. And then we'll just connect the dots. Draw your arrows. And then last but not least, we'll write in our equation. Y is equal to 9/5 C plus 32. And it's not Y, it's F. And we're done. Let's see how many more, a few more examples. Okay. Let's see, I might have 2 students read this for me. So Natalie, I'm gonna have you read the purple. And then Alexandra, I'll have you read the pink.
Cost of running some types of business has two components, a fixed cost and a variable cost. The fixed cost is always the same regardless of how many units are produced. This is the cost of rent, insurance, equipment, advertising, and other items that must be paid regularly.
Thank you.
The variable cost depends on the number of units produced. It is for the material and labor needed to produce each item.
Great, thank you guys. And so here's another applicable example. We have Sam drives a delivery van. The equation is represented as our C, our weekly cost in dollars, is equal to 0.5 M, which represents the number of miles that he drives, plus the initial value, aka our intercept, our C intercept, or our Y intercept, which is 60. So part A asks us to find Sam's cost for a week when he drives 0 miles. So our M is equal to 0. We plug it in. 0.5 times 0 plus 60. Anything times 0 is 0. So we just get our cost is $60. It's our initial cost. Our C intercept, 0, 60. Once you start getting the hang of this, you can sort of combine steps, right? We're gonna plot 0, 60 on our graph, sort of get ahead. Now let's answer part B. We have find the cost for a week when he drives 250 miles. So now our M is equal to 250. And so we plug it in. We have 0.5, which is just 1/2 of 250 plus 60. Half of 250 is just 125. And 125 plus 60 gives you $185, which means another coordinate point, which we won't be able to graph because these are very large numbers, but 250, 185. Part C, we have interpret the slope and the C intercept of the equation. Well, our slope is just 0.5, which is 1/2. And then our C intercept, our starting value, our initial costs without even driving any miles, is $60. And as we drive additional miles, for every 1 mile we drive, we're adding on some more money, or really right? For every 0.5, we're adding on an additional dollar. So last but not least, let's just graph this. We plotted our y-intercept, but now let's use the slope to plot some additional points. So we're going up 1 over 2. Up 1 over 2. We'll do one more, up 1 over 2. I'm going to go ahead and connect the dots and then write our equation of our line after we put in our arrows. So we have C is equal to 0.5 m plus 60, and we're done. This is our last objective for today. We have our formal notes on parallel lines. Again, parallel lines mean that you have the same slope. The lines do not intersect, which means you need to have a different y-intercept. Different y, or parallel vertical lines have different x-intercepts. It's just a famous fact. Whereas everything else, we have our different y-intercepts. So let's practice this. We want to use the slopes and y-intercepts to determine if we have parallel lines. So part A, we're given two equations. Always put them into our slope-intercept, our y equals mx plus b form. That way you can easily identify what your slope and what your y-intercepts are. Lucky for us, that second one is already in your slope-intercept, so we know what our slope and what our y-intercept is here. But the second one, we're going to have to do some inverse operations. I'm going to go ahead and add 2y to both sides and then subtract 6 from both sides. So we're looking at 2y is equal to 3x minus 6. And then lastly, I'm going to go ahead and divide both sides by 2. Bless you. So we have 3 over 2x, and then 6 divided by 2 is just 3. Which means our slope here is 3 over 2, and our y-intercept is -3. Do we have the same slope? Do we have a different y-intercept? Therefore, what do we know? These two lines are they're parallel. And the short script for parallel is just two parallel lines that have like these half arrows. Let's try that second one. So that y equals 2x minus 3. We already have our slope is 2. Our y-intercept is -3. Then we have -6x plus 3y equals -9. We're going to go ahead and add 6x to both sides. So we're looking at 3y is equal to 6x minus 9. And then we're going to divide both sides by 3. So we have y is equal to 6 over 3 is just 2x. 9 over 3 is 3, which tells us that our slope here is 2, our y-intercept is -3. Do we have the same slope? Do we have the same y-intercept? Are these lines parallel? They are not, because the y-intercept is the same. These are just identical lines. So therefore, we do not have parallel lines, although the slopes are the same. So are the y-intercepts, which is bad. Let's look at example 10. We have used slopes and y-intercepts to determine if the lines are parallel. Now we're looking at just vertical and horizontal lines. So y equals -4 versus y equals 3. These are two horizontal lines. If we were to plot these, are these parallel? They are. -4, right, is here. +3 is up here. We have two parallel lines. They'll never touch. So therefore, yes. What about part B? Two vertical lines. So once again, yes. Therefore, yes, they are parallel. And our last definition for today are our perpendicular lines, how they have negative reciprocal slopes. The y-intercepts can be the same in this case. So let's look at our last example for the day. We want to figure out, are these lines perpendicular? -5x minus 4 gives us a slope of -5 and a y-intercept of -4 versus x minus 5y equals 5. Let's put this into our slope-intercept form. So we're going to add 5y to both sides and subtract both sides by 5. So now we're looking at 5y is equal to x minus 5. Let's divide both sides by 5. So our y is equal to 1/5 x minus 1, which tells us our slope is 1/5, and our y-intercept is -1. We're really just honing in on our slopes here. Are these negative reciprocals? -5 as a fraction is -5/1. If we flip it and multiply by -1, will we get 1/5? Yes. Therefore, yes, these are perpendicular. And then lastly, we have our part B. 7x plus 2y is equal to 3. Subtract both sides by 7x. Now we're looking at 2y is equal to -7x plus 3. And we're going to go ahead and divide both sides by 2. Y is equal to -7/2x plus 3/2. Our slope here is -7/2. Our y-intercept is 3/2. Let's compare this to our 2x plus 7y. Shrink this. So we have 2x plus 7y is equal to 5. Subtract both sides by 2x. We have 7y is equal to 5 minus, or let's put the negative 2x first. And divide both sides by 7. Looking at negative 2 over 7x plus 5 over 7, which tells us that our slope here is negative 2 over 7, and our y-intercept is 5 over 7. Again, we just have to hone in on these y-intercepts. Are these negative reciprocals? No, they're both negative here. So they are not perpendicular. Right. This does conclude our 3.2 section.